Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Dielectric Properties, Lecture 2 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So first we will see the mechanism and different types of polarization. Next we will go to we will see electronic polarization. Then what is ionic polarization, orientation polarization and the static dielectric of gases. So to start with electronic polarizability. So what happens in a free atom, the charge distribution is such that the dipole moment in the absence of an external field vanishes. The center of gravity of the electron distribution coincides with the nucleus. Consider now an atom in a static homogeneous external field E. The force exerted on the positive nucleus will then be oppositely directed to the forces exerted on the electrons. As a result, the external field tends to draw the center of gravity of electrons away from the nucleus. On the other hand, the attractive forces between the electrons and the nucleus tend to preserve a vanishing dipole moment in the atom. Consequently, an equilibrium situation is reached in which the atom bears a finite dipole moment. This has been represented schematically in figure 1. The resulting dipole moment is thus induced by the field as a result of an elastic displacement of the electronic charge distribution relative to the nucleus. The induced moment may be represented by mu induced, which is equal to alpha E times E, where alpha E is called the electronic polarizability of the atom. It should be noted that equation 1 is actually only the first term of a power series in the field strength for the usual fields employed in dielectric measurements. However, 1 is a very good approximation. From the figure A, we see that it's a schematic illustration of the displacement of the electron orbit relative to the nucleus for a hydrogen atom under influence of an external field E, and in B, simplified model for estimating the magnitude of the electronic polarizability of an atom as described in the text. To obtain an idea of the magnitude of alpha E, consider the following simplified model. Suppose the atom is represented by a nucleus of charge Ze and a homogeneous negative charge distribution inside a sphere of radius r. If the nucleus is displaced over a distance d under the influence of the field E as shown in figure 2, it can be shown through laws of electrostatics that when a field E is applied to this atom, the nucleus is displaced from the center of sphere by a distance d equals to 4 pi epsilon 0 r cube by Jd into E, where r is the radius of the sphere, the atomic radius, and Ze is the nuclear charge. The atom is thus polarized, and the dipole moment mu is equal to Z into E Jd into D. If we put the value of D from equation 2, we get mu is equal to Ze into 4 pi epsilon 0 r cube by Jd into E. From comparison of equation 1 and 4, we get alpha is equal to 4 pi epsilon 0 r cube. If we substitute the typical value r is equal to 10 to the power minus 10 meter, we find that alpha E is approximately equal to 10 to the power minus 41 farad into meter. So table 1 summarizes the electronic polarizabilities for some inert gases and closed shell alkali and halogenic ions in units of 10 to the power minus 40 farad into meter square. So we have many inert gases like helium, neon, argon, krypton and xenon, and you can see that the polarizability varies from 0.18 for helium to 2.2 for krypton, and similarly for ions like lithium ions it is 0.018, whereas for cesium Cs it is 2.20, and for iodinium we have polarizability is 5.5. It will be evident that in general atoms with many electrons tend to have a larger polarizability than those with few electrons. Electrons in the outer electronic cells will contribute more to alpha E than electrons in the inner cells, because the former are not so strongly bound to the nucleus as the latter. Positive ions, therefore, will have relatively small polarizabilities compared with the corresponding neutral atoms. For negative ions, the reverse is true. Ionic polarizability. So far, we have considered only simple atoms and ions. For molecules, one is faced with two more possible influences of an external field. 1. Molecules may have permanent dipole moments which may be aligned in an external field, or the distances between the ions or atoms may be influenced by an external field. For example, a molecule such as HCl may in first approximation be considered to consist of two ions. The permanent dipole moment is thus equal to the effective charge for ion times the separation of the ions. Symmetric molecules like H2, carbon dioxide, CCl4, etc. evidently have no permanent dipole moment. An external electric field will tend to orient permanent dipole along the field direction, and one speaks of orientational polarization. In molecules as well as in atoms, an external field will displace the electrons with respect to the corresponding nuclei. Over and above this, however, a displacement of atoms or ions within the molecule may be caused by an external field. For example, in an HCl molecule, an external field will change the inter-ionic distance to some extent, leading to a change in the dipole moment. Similarly, in a molecule like CCl4, which has no permanent dipole moment, a change in the bond angles between the CCl groups will produce a dipole moment, because each of these groups by itself does have a dipole moment. This kind of induced polarization is called atomic or ionic polarization, because it is a consequence of the displacement of atoms within the molecule. The induced electric dipole moment resulting from elastic displacement of ions within the molecule may again be represented by an expression of the type equation 5 by replacing alpha E by the atomic polarizability alpha I. It should be noted that alpha I refers to an average overall possible orientations of the molecule with respect to the field. In lecture 1, it will be shown that alpha I may be considered a constant up to frequencies in the infrared spectrum. For most molecules, alpha I is of the order of 10% of alpha E. This figure 2 represents a sodium chloride, that is NaCl chain in the NaCl crystal without an applied field. Average or net dipole moment for ion is 0. In figure 2b, it is shown in the presence of an applied field, the ions become slightly displaced, which leads to a net average dipole moment for ion. Orientational or dipolar polarization. Certain molecules possesses permanent dipole moments. For example, HCl molecule shown in figure 3a. It has a permanent dipole moment mu0 from the Cl minus ion to the H plus ion. In the liquid or gas phase, these molecules, in the absence of an electric field, are randomly oriented as a result of thermal agitation, as shown in figure 3b. When an electric field is applied, E tries to align the dipoles parallel to itself, as depicted in figure 3c. The Cl minus and H plus charges experience forces in opposite direction, but the nearly rigid bond between Cl minus and H plus holds them together, which means that the molecule experiences a torque R about its center of mass. This torque acts to rotate the molecule to align mu0 with E. However, due to their thermal energy, the molecules move around randomly and collide with each other and with the walls of the container. These collisions destroy the dipole alignments. Thus, the thermal energy tries to randomize the orientation of the dipole moments. A snapshot of the dipoles in the material in the presence of a field can be pictured as in figure 3D, in which the dipoles have different orientations. There is nonetheless a net average dipole moment per molecule mu average that is finite and is directed along the field. Thus, the material exhibits net polarization, which leads to a dielectric constant that is determined by this orientational polarization. To find the induced average dipole moment mu average along E, we need to know the average potential energy E dipole of a dipole placed in a field E and how this compares with the average thermal energy 5/2 kT per molecule as in the present case of 5 degrees of freedom. E dipole represents the average external work done by the field in aligning the dipoles with the field. If 5/2 kT is much greater than E dipole, then the average thermal energy of collisions will prevent any dipole alignment with the field. If, however, E dipole is much greater than 5/2 kT, then the thermal energy is insufficient to destroy the dipole alignments. A dipole at an angle theta, as shown in the above figure, to the field experiences a torque tau that tries to rotate it, as shown in figure 3c. Work done dW by the field in rotating the dipole by d theta is tau times d theta. This work dW represents a small change dE in the potential energy of the dipole. No work is done if the dipole is already aligned with E when theta is equal to 0, which corresponds to the minimum in PE. On the other hand, maximum work is done when the torque has to rotate the dipole from theta is equal to 180 degree to theta is equal to 0 degree, either clockwise or counterclockwise, it does not matter. Let us define the potential energy of a dipole making a 90 degree angle with the external field as 0. The potential energy corresponding to an angle theta given between mu and E is then equal to mu E cos theta is equal to mu dot E. According to statistical mechanics, the polarizability for a dipole to make an angle between theta and d theta with the electric field is then proportional to 2 pi sin theta d theta exponential of mu E cos theta by kT, which is the solid angle between theta and theta plus d theta. Hence, the average component of the dipole moment along the field direction is equal to mu average over cos theta is equal to integration over 0 to theta is equal to 0 to pi mu cos theta sin theta d theta exponential of mu E cos theta by kT divided by integration over theta is equal to 0 to pi sin theta d theta exponential over mu E cos theta by kT. To evaluate the integrals, let us put mu E cos theta by kT is equal to x and mu E by kT is equal to a. We then obtain the average value of cos theta is equal to 1 by a integration over minus a to a x into e to the power x dx divided by integration over minus a to a ex into dx is equal to e to the power a plus e to the power minus a divided by e to the power a minus e to the power minus a minus 1 by a, which we represent as LA. The function LA is called the Langevin function. Since this formula was first derived by Langevin in 1905 in connection with the theory of paramagnetism. In figure 4, LA has been plotted as a function of A is equal to mu by kT. Note that for very large values of A, that is for high field strengths, the function approaches the saturation value unity. This situation would correspond to complete alignment of the dipoles in the field direction, because then mu into average over cos theta is equal to mu. As long as the field strength is not too high and the temperature in figures, the Langevin function LA not too low, the situation may be for A is less than 1. The slope is 1 by 3, strongly simplified by making the approximation A is very less than equal to 1 or mu dot E is very less than kT. Under these circumstances, the Langevin function LA is equal to A by 3, so that mu average over cos theta is equal to mu square by 3 kt into E, for mu dot E is very less than kt. As an example of the condition implied in 10, consider a field of 3000 volts per centimeter. The dipole moment P of a molecule is of the order of 10 to the power minus 10 USU of charge times 10 to the power minus 8 cm, that is about 10 to the power minus 18 CGS units. So that mu dot E is equivalent to 10 to the power minus 17 in CGS units. On the other hand, Kt at room temperature is of the order of 10 to the power minus 14 org, and for this example the condition is certainly satisfied. In this example, saturation would be approached only in the vicinity of 1 degree Kelvin. It may be noted that the quantum mechanical treatment of this problem leads essentially to the same results as obtained here. The static dielectric constant of gases. We are now in a position to give an atomic interpretation of the static dielectric constant of a gas. It will be assumed that the number of molecules per unit volume is small enough so that the interaction between them may be neglected. In that case, the field acting at the location of a particular molecule is to a good approximation equal to the applied field E. Suppose the gas contains n molecules per unit volume. The properties of the molecules will be characterized by an electronic polarizability alpha E, an ionic polarizability alpha I, and a permanent dipole moment mu. From the discussions in the preceding two sections, it follows that as a result of the external field E, there will exist a resulting dipole moment for unit volume or polarization, that is P is equal to summation over alpha E plus alpha I plus mu square by 3 kt times E. Note that only permanent dipole moment gives a temperature dependent contribution, because alpha E and alpha I are essentially independent of T. If the gas fills the space between two capacitor plates of area A and separation D, the total dipole moment between the plates will be equal to mu total is equal to P times A times D. So students, let us summarize what we have learnt in this module. So we considered mechanisms of polarization and determined polarizability. We learnt what is electronic polarization, which induces dipoles, and next is ionic polarization, which shifts the existing ions, the orientation polarization, which rotates existing dipoles, and the static dielectric constant of gases that has been discussed in detail. Thank you.